class, start off with a, say, 10 meter per second velocity and verify that your calculate the initial kinetic energy, and then make sure that you run this through and make sure that the change in kinetic energy is still 1500 joules. So your final kinetic energy, whatever your initial was, plus 1500 joules. In physics 100, I would give you the initial kinetic, well, I'd give you calculate the initial kinetic energy, but I wouldn't have you work through it this way. I could say initially we have 1000 joules of kinetic energy, we do this much work, what's the final velocity? And then you would have to take 1000 plus 1500 to get 2500, and then set 2500 equals 1/2 mass times v squared. All right, energy transfers. Energy is neither created nor destroyed. It merely changes form. So we had F equals ma, and moment is conserved. Now we have energy is conserved. Energy is conserved. Brains are tasty. By the way, the energy is conserved zombie, normally you have to shoot them twice. Those you have to shoot 3 times because they have more energy because it's conserved. All right, so energy is conserved. So we can transfer back and forth between different forms of kinetic, different forms of potential, or just straight back and forth between kinetic and potential. However, the total energy, unless we do work to the system, the total energy will always stay the same. So if I take a pin and I throw it up in the air, now while it's in the air, there's going to be no work done on the pin if we ignore the fact that gravity does work, and we include that just with the total energy. That's why I like to do it that way. There's no work other than by gravity as the pin's in the air. So initially it has some amount of kinetic energy, and as it goes upwards it slows down, which means it's losing kinetic energy. But as it goes higher, it's gaining gravitational energy. So in other words, it's converting its kinetic energy to gravitational potential energy. There's different forms of potential gravity as well. Now, when it gets to the top, how much kinetic energy does it have at the top? Think about that. Is it moving? What's its velocity? Run through the equation. Should be pretty straightforward. Velocity is 0. So the kinetic energy is 0. So in other words, all the energy has been converted to potential. And as it falls, it's going to convert potential back to kinetic. And when it, just before it hits the ground, it's going to have no potential energy because its height is 0. It's going to convert it all to kinetic. Now, at this point, you're going, wait a minute, you haven't taught me the equation for potential energy yet. How do you expect me to know this and that? Okay, well, we're going to get there. So, let's derive the gravitational potential energy. Work equals force times distance. What's the force of gravity? No, it's not G. Try it. You left something out. That's right, it's mg. I feel like I'm on the PBS station all of a sudden. Today's lecture is brought to you by the number square root of 22 over 7. And the letter delta. Okay. So, the gravitational force is mg, the distance is the height, so the potential energy for gravity is mass times gravity times height. Sorry, play pen. So, but this is gravitational potential energy, mgh. All other forms of potential energy are usually denoted with the letter U, just to be really confusing. So, for example, spring potential is U equals 1/2 kx squared, which equation we don't really use much in physics 100, but in the other physics classes you will. So if we take our potential, mgh, plus our initial kinetic energy, initial potential plus initial kinetic, this gives us our total energy. It's kind of like having our total net worth. We have it split up between checking and savings, or savings and checking. Kind of tough to tell which one's which. And that total won't change. We're just going to transfer money back and forth, unless we do work. Now, work is a deposit. So if we do positive work, we have a positive deposit. If we have negative work, we have a negative deposit. Otherwise, there's a withdrawal. So the only way to change my total energy is to do work. So air resistance would do work. If I throw a ball up in the air and it comes back down, air resistance would decrease my total energy. No air resistance means my total energy would remain the same. So I have some amount of total energy. At the maximum height, my total energy is all in potential. Near the ground, it's all in kinetic. And anywhere in between, it's split between potential and kinetic. So this is just what I just told you. So let's do an example. All right, I'm holding a 2 kilogram ball at a height of 0.6 meters. So the questions are going to be as follows. A, what is the initial kinetic or initial potential energy? B, what is my initial total energy? Now I have no kinetic because it's motionless. C, just before the ball hits the ground, how much kinetic energy will I have? And D, what will the velocity be? So I change it from what's written below this. A, find the potential energy. B, find the total energy. C, what will the kinetic energy be just before? And the reason I say just before is because if I ask for what's the kinetic energy, after when the ball has hit the ground, everyone will say 0. So I say just before because the ground hasn't stopped it yet. So it's still height 0, but the ball just hasn't run into the ground yet, and the ground hasn't stopped it. I know that's a little bit confusing, but otherwise I find so many people get confused, just randomly put 0 that I have to emphasize that it's not 0. Okay. And the D, what is the velocity? No, the answer is not 0. Okay. Solve these 4. Go. All right, A and B are level 1 problems. C is a level 2 because it requires a concept. And then D is a level 1 because once you have your answer for C, you just plug and play. Okay. So let's do this. Potential energy equals mgh, which equals 0.6 m. Sorry, 2. I put in the height for mass. 2 kilograms. And we're going to use 10 in this class just to make math easier. Now, by the way, in this equation, G and H are both downwards, so you do not have to worry about direction. The gravitational potential will always be positive unless you are underground, in which case your height would be negative. So we're okay. We don't have to put in the direction. Like so. 2 times 10 is 20, times 0.6 is 12 joules. All right. Total energy. It's kinetic plus potential, which is 12 joules plus my kinetic, 1/2 mv squared. 1/2 m0 squared is 0. So my total energy is 12. How much kinetic energy do I have just before it hits the ground? In this case, I'm going to always set up the full equation when in doubt. Total energy equals 12 joules equals Ke plus Pe. In this case, my Pe is going to be 0. So that means my kinetic energy is going to be 12 joules. So 12 joules equals 1/2 mv squared. I'll leave it to you to do the algebra. I multiply by 2 and divide by m. So I'm going to have 24 joules over m equals v squared. So I take the square root. And the mass, of course, was 0.6. So I have the square root of 40, which is approximately 6.3 meters per second. Hopefully I didn't freak you out too much. By the way, if you're wondering how I do square roots like that, I use what's called something based on the monomial theorem. I use a big number plus a little number squared, which gives me a big number squared, which in this case was 6, which gives me 36, plus a little number that I'm trying to solve. When I do this, I have 2n times n. This equals 40. So 12n. So that means that 12n equals 4. And I just divide, this is about 1/3. So 6.3. Well, 6.333. Then I would do an iteration where notice I left off little n squared. If n is, little n is much smaller than big N, and n squared is, you can ignore it, it becomes an error term. So I have little n squared divided by 2 big N now equals I set that up, and so this is 1/9 divided by 12, it's 0.01. In fact, it would be negative, so it would, that's 900, so it'll be 32. Now, if you didn't follow that, don't worry. Usually you have a calculator, but if your calculator breaks and you have to do square roots, you can do this. Maybe. So, that solves all of that. Moving on. Oh, that was. Let's do another problem. One more problem. Let's do one that's more of a level 2 problem from the get-go. This is more like one you would see on the test. Right, so this is about as tough as I can throw at you. Well, actually, the only way I can throw anything more difficult is just by including bulk. So that's probably what we'll see over the exam. So like this one would work. I'm going to be on the top of a roof, which is 3 meters up. And that includes, my hand. So my hand is 3 meters above the ground when I throw the ball. When I throw the ball, I'm going to throw it kind of upwards. So ignore horizontal here. With a velocity of 17, let's just call it, let's make the math easier. Let's call it 20 meters per second up. And the mass of the ball is 2 kilograms. So here's what I want you to calculate. I want you to calculate A, the total energy. I want you to calculate B, the max height. So remember, at some point, the kinetic energy is going to go away. C, I want you to calculate the velocity when it hits the ground, or just before it hits the ground. So it's not 0. Now, you should get an answer for C that is bigger than 20, because it's going to go up, then come back down and fall that extra 3 meters to the ground. All right, so go ahead and calculate those. Go. All right, and for A, make sure you include both potential and kinetic. Go. For B, again, what is the kinetic energy? Set up the full total energy equation. Solve for that. Go. For C, how much is your potential? Set up the total energy equation, just like in total force or total momentum equations. Go. All right, at this point, you should have all 3 of them, hopefully. All right, so total energy equals mgh plus 1/2 mv squared, potential plus kinetic. So that is 2 times 10 times 3. This is all going to be joules, plus 1/2 times 2 times 20 times 20. So this is 60 joules plus, that's 400 joules. So that's 460 joules is my total energy. Now this total energy is going to stay my total energy for the duration of the problem because nothing does work to the ball. Now if air resistance did work to the ball, all it would do is decrease my total energy. So that when the ball hit the ground, it would have less than this amount of energy, which means it would hit the ground slower than it would otherwise. All right, so maximum height. At the maximum height, 460 joules, which is my total, equals potential plus kinetic. But at the maximum height, my kinetic is 0. I have transferred all of my energy to potential. So mgh. So divide by gh, mg, and my height equals 460 divided by mg, which is 2 times 10, that's 20, and so that means my maximum height is 23 meters. If I went too fast, go back, watch it again. So mg, 2 times 10, so that's 20, 460 divided by 20 is 23. All right, hopefully you got that as well. Now, when it hits the ground, we're going to set up the same equation again. Total energy. A lot of energy is about total energy, at least the way I like to set it up. That way it remains consistent. Even if you're doing a different class, you're doing a calc-based class or a trig-based class, you're going to do this a lot. You're going to have the total energy. You're going to put that energy into different forms quite a bit. You'll have a car at the top of a hill, it'll roll down the hill, run through some sticky stuff, and hit a spring. That's all energy. You're converting gravitational potential to kinetic, doing some work with friction to decrease your total energy, and then you convert that kinetic energy back to a spring potential. So it's all a series of energy problems there. All right, so potential plus kinetic, and I'm writing out the kinetic for here because my potential is 0 and the total was 460. So that means that my velocity equals square root of 2 times 460 divided by my mass. How did I get this? Well, 460 equals 1/2 mv squared multiplied by 2, divide by my mass, and I've got my answer. So the square root of 460, because the 2's cancel, is approximately 21.5 meters per second. And of course, this one is going to be down. I just got the direction from the just thinking it through, because it's going to be going down towards the ground. Okay, so that's my answer. And that's just about as difficult as I can make it for this kind of a problem. I can also throw in a little bit of air resistance and how you calculate how that much changes. So if I had, say, I declared that air resistance did minus 100 joules work during this process, then your final energy would be 360 instead of 460. And then that would change this a little bit. So, it'd be 18.5 instead of 21.5. All right, so that is all for energy. We've seen how energy, we actually know a little bit more about energy. Energy in the future is going to become even more important than it is today. The reason being is that as we take our place among the stars and we actually try to move out of our own solar system, this is 100, 200, 300 years in the future. It turns out that takes a lot of energy. It takes as much energy to run a single spacecraft at close to the speed of light, which is what you would need to do to get to stars, other stars, in reasonable time frames, as the United States uses in 100 years. And so energy is going to be exponentially more important in the future. And so with our limited resources and the effects on the environment that those limited resources have when we use them, we really need to be able to have cheap, emphasis on the word cheap, energy that is renewable. So if you want to make $1 trillion, you want to be the first trillionaire in the world, the way to do that is to make a solar panel that is 4 times more cost efficient than the current ones, because then solar power will be more economically efficient than gas. And when that happens, there'll be a mass migration to solar power. And you can be the one to reap the rewards. All right, so so to wrap up, we've seen how the energy is used, is useful, transfer between forms, and we discovered how you calculate work, power, kinetic energy, potential energy, and how to transfer back and forth between those. We've learned that energy is conserved, and so the total energy stays the same unless you do work. And we've examined slightly about energy in the future. All right, so that is all for this lecture. Hopefully this chapter is a refresher after the difficulties of the last chapter. And I will see you all in class.